This experiment requires 2 meter sticks for measuring length, tape to keep the rulers in place, the Huddle application for measuring time, 2 balls of different sizes and masses to analyze different variables, and a scale to record the mass of the balls. The energy changes in the system as seen in the following setup: 90 centimeters, 70 centimeters, and 50 centimeters. We will perform 3 trials of each type of setup in order to achieve more precision in our calculations by averaging our data from multiple trials. In each trial, we will measure the time it takes for the ball to hit the ground from the designated drop height. We will also measure the time it takes for the ball to bounce back up to its peak height, as well as recording the peak itself. Using the calculated averages of these values, we will be able to calculate the downwards and upwards velocity of the ball using the equation velocity equals change in position over change in time. By using the scale to record the mass of the ball in conjunction with the calculated velocities, we are also able to calculate the kinetic and gravitational potential energies of the system, utilizing the equations kinetic energy equals 1/2 mass times velocity squared, and the gravitational potential energy equals mass times the gravitational constant times change in height.
Hey Dr. Weiner, what's up?
So as we can see from our final data tables of kinetic energy for each ball going up and down, kinetic energy is actually less on the way back up than on the way down.
Wait, why would kinetic energy be less? Isn't it conserved?
That's a very good question, Sydney. So this is actually an inelastic collision in which energy is lost to heat and sound, and basically when the ball hits the ground, there's some energy lost to heat, which you could see if you had a thermal imaging camera, and then there's some energy lost to sound, which you can actually hear when you put your ear up to it.
But Eva...
Excuse me, Sydney, but does this look like crossroads to you?
Sorry, Dr. Weiner, why are the kinetic energy values for the heavier ball greater?
Because, Sydney, the kinetic energy formula is 1/2 the mass times the velocity squared, which means that mass is taken directly into account. And because the heavier ball obviously has a greater mass, therefore this value is going to be greater. And heavier balls also fall faster, which means that the velocity is also going to be greater.
Oh, I think I'm starting to get it!
That's good considering how many of my lunch periods you take up. Okay, so next we're going to talk about gravitational potential energy. And as you can see, that is also less on the way back up. So do you think you could explain to me why that is?
I'll try, but I think it might be wrong. Is it because energy is lost to heat and sound when the ball hits the floor, which then decreases kinetic energy, which makes the ball travel less on the way back up?
Yes, that's technically correct, but why would that decrease the gravitational potential energy?
Maybe because gravitational potential energy is the work needed to move an object from its original position to its final position, and if the new original position is not as high up, not as much work needs to be done on the object to move it back down to the floor.
Yes, that's surprisingly spot on.
And I'm guessing that the gravitational potential energy is greater for the bigger ball because more work is required to move it.
Well, they should just take away my PhD from Harvard and give it to you, Sydney. You get an A for the semester.